In the vast expanse of interstellar space, an object named 3 Atlas emerged, defying all known traits of comets. Its metallic surface, rich in nickel and chromium, and its geometric depressions captured by the Mauna Kea Observatory on November 10, 2025, baffled astronomers. Its erratic trajectory and dense, structured tail of ionized particles suggested a magnetic field, an impossibility for natural comets. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it on X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Spectroscopic analysis of 3 Atlas detected exotic compounds challenging our understanding of physics. Its tail, studied intensely, twisted and realigned with unprecedented coherence, hinting at active control. Observations from the European Space Agency's solar orbiter raised questions about its origins, natural or artificial. Within weeks, 3 Atlas transformed, emitting brief flashes of light detected by the Atacama Large Millimeter Array. Telescopes worldwide revealed its complex surface, with craters, ridges, and possible artificial structures. The James Webb Space Telescope detected thermal variations, suggesting active processes beneath its surface. As 3 Atlas approached the Sun, theories emerged. Some proposed it was an ancient civilization's probe or a Bracewell probe, a self-repairing autonomous spacecraft. Its trajectory adjustments hinted at technological sophistication far beyond human capability. Time is running out as 3 Atlas recedes into the interstellar void. Astronomers worldwide are working tirelessly to decipher its secrets. At the Jet Propulsion Laboratory, teams analyze its trajectory for signs of intelligent control, while astrobiologists study its composition for indicators of life. This is the story of humanity's encounter with an interstellar enigma. 3 Atlas challenges our understanding of the cosmos and leaves us in awe of the vastness of the universe. As it fades, it serves as a beacon, guiding us towards the unknown and the wonders that await. Part 1. The Impossible Visitor. What if the most extraordinary objects in the universe are the ones we least expect? On October 30th, 2025, 3 Atlas reached perihelion, its closest approach to the Sun. For 9 tense days it was hidden from our view, obscured by the blinding glare of our star. Ground-based telescopes from the Canary Islands Tide Observatory to the Atacama Desert's ALMA Array were blinded by the Sun's brilliance. Even space-based instruments like NASA's Solar Dynamics Observatory struggled to capture more than fleeting glimpses of its behavior. The Sun's corona, a plasma atmosphere that extends millions of kilometers into space, created a veil of interference, distorting observations and leaving astronomers worldwide in a state of anxious anticipation. The brief window of perihelion could reveal or conceal the object's true nature, and the countdown to its re-emergence was marked by a palpable sense of urgency. When 3 Atlas finally reappeared on November 10th, the images captured by the Virtual Telescope project stunned the scientific community. The object seemed to defy the laws of cometary physics. Its ion tail, a stream of ionized gas blown back by the solar wind, was unlike anything ever recorded. It wasn't a simple, uniform stream, but a complex structure of curved filaments and intricate patterns, stretching an astonishing 12 million kilometers into space, almost 3 times the width of the Moon's orbit around the Earth. The tail's luminosity fluctuated dramatically, pulsing with bursts of energy that suggested internal processes far more dynamic than any observed in traditional comets. At its brightest, the tail outshone the entire Comet 4-1p Tuttle-Giacobini Cressack by a factor of 10. Despite 3 Atlas being less than half its size, the spectra of light emitted by the tail revealed traces of elements never before detected in cometary environments. Exotic isotopes of hydrogen and helium glowed in ultraviolet wavelengths, while heavier elements like iron and nickel, ionized and accelerated to unprecedented velocities, left their signatures in the infrared. These elements were not mere passive components, but seemed to be actively involved in the tail's behavior, as if part of a larger, self-regulating system. The data poured in from observatories around the globe. The Subaru telescope in Hawaii detected fluctuations in the tail's magnetic field, while the European Southern Observatory's VLT captured high-resolution images of the tail's filaments twisting and untwisting in real time. This wasn't just a comet. It was a cosmic riddle written in light, gas and motion. Observation. The tail's behavior suggested a source of energy far beyond what solar radiation alone could provide. Theories emerged about the possibility of an internal energy source, perhaps a form of nuclear or even antimatter reaction, though such ideas bordered on the fantastical. The object's nucleus, estimated to be no larger than 300 meters in diameter, seemed incapable of sustaining such processes, yet the data refused to align with conventional models. The tail's energy output was calculated to be equivalent to a small star, and its structural integrity defied the expected effects of solar wind erosion. Some researchers even proposed that the tail itself might be a byproduct of an unknown propulsion system, though this remained purely speculative. Interpretation. Some researchers proposed that 3 Atlas might not be a natural object at all. Its trajectory, originating from outside the solar system, was already a point of intrigue. Now its behavior at perihelion raised questions about its composition and purpose. Could it be an artificial construct designed to withstand the punishing conditions of the inner solar system? The idea seemed far-fetched, but the evidence was increasingly difficult to ignore. The object's velocity and trajectory had been meticulously calculated, revealing that it had likely been traveling through interstellar space for millions of years. The chances of such an object entering our solar system by pure coincidence were astronomically low, less than 1 in a trillion, according to simulations run by the SETI Institute. Known. 3 Atlas survived perihelion intact and displayed intense activity. Its ion tail exhibited unprecedented complexity and energy output. Spectroscopic analysis revealed the presence of unexpected elements in ionized states. The object's trajectory and behavior suggested it was not a typical comet or asteroid. Unknown. What caused its transformation during the days it was hidden behind the sun? Was the object natural or artificial in origin? What powered its extraordinary behavior? And why did it seem to defy every expectation of cometary physics? The mystery deepens as we probe further. What other changes occurred during those critical days? Radar observations from the Arecibo Observatory in Puerto Rico, though limited by the objects. Distance and angle hinted at structural anomalies in its nucleus. The data suggested a surface of extreme hardness, possibly metallic, with a reflectivity comparable to polished titanium. The object's shape was equally perplexing, defying the typical potato-like form of most comets and asteroids. Instead, it appeared almost geometric, with sharp edges and symmetrical features that seemed too precise to be the work of nature alone. Some researchers compared its silhouette to a polyhedron, while others noted similarities to the precise angles found in certain crystalline structures. As 3 Atlas continued its journey outward from the Sun, its behavior remained unpredictable. Its rotation, initially estimated at about 5.2 hours, began to slow, as if something were counteracting its spin. By December 1st, its rotation had slowed to 7.4 hours, a change that defied the laws of angular momentum. At the same time, its brightness fluctuated in ways that suggested deliberate modulation, rather than random outgassing. Some astronomers even reported detecting faint, pulsed radio signals emanating from the object, though the data was too fragmented to confirm their origin or meaning. The signals appeared to follow a repeating pattern, with intervals of 2.7 seconds between pulses. This was not the erratic behavior of a natural object, but something far more deliberate, and perhaps intelligent. Speculation. If 3 Atlas were artificial, its creators would have needed technology far beyond our own. The ability to build an object capable of surviving interstellar travel, let alone the extremes of perihelion, would require materials and energy sources unknown to human science. Equally puzzling was the question of intent. Why send such an object into our solar system? Was it a probe, a message, or something else entirely? Some researchers drew comparisons to the Voyager probes, launched by NASA in the 1970s to explore the outer solar system and beyond. Others speculated that 3 Atlas might be a remnant of an ancient civilization, a relic adrift in the cosmos for eons. The implications were staggering, and the scientific community approached the possibility with a mix of excitement and caution. As 3 Atlas receded from view, its secrets remained locked within its enigmatic structure, yet the data it left behind would fuel years of research, debate, and wonder. For astronomers, the object was more than just a scientific curiosity. It was a reminder of how little we understand about the universe and the possibilities it contains. The hunt for answers would continue, driven by the relentless curiosity that has defined human exploration since the dawn of time. But for now, 3 Atlas remained the impossible visitor, a cosmic question that refused to be solved, a beacon of mystery in the vast and unknowable expanse of the universe. Its story was far from over, and its legacy would forever change our understanding of what lies beyond the stars. Part 2. The geometry problem. What if the greatest discoveries are hidden not by distance but by perspective? To understand 3 Atlas, we must first understand the geometry of its encounter. Comets are 3-dimensional objects moving through a 3-dimensional solar system. But our view from Earth flattens this reality, limiting what we can observe. Astronomers often rely on a single plane of observation, as if watching a cosmic play from a fixed seat in a vast, dark theatre. This perspective can obscure critical details, especially when the object in question is as dynamic and complex as a comet. 3 Atlas was no exception. During its closest approach to the Sun, known as perihelion, its ion tail, a luminous streak of charged particles stretching millions of kilometers, was pointing almost directly away from us, hidden behind the comet's nucleus and the dense cloud of gas and dust surrounding it. We couldn't see it, not because it didn't exist, but because we were looking from the wrong angle. The geometry of this encounter was further complicated by the comet's trajectory. 3 Atlas was on a highly elliptical orbit, diving toward the Sun from the outer reaches of the solar system. At perihelion, it was travelling at speeds exceeding 60 kilometers per second, making it one of the fastest moving objects ever observed in our solar system. To put this into perspective, this speed is roughly 216,000 kilometers per hour, or about 60 times faster than a bullet fired from a high-powered rifle. This incredible velocity, combined with its angle of approach, meant that the comet's features were changing rapidly, but our fixed perspective on Earth kept many of these changes hidden. The nucleus, a jagged chunk of ice and rock estimated to be just 1.2 kilometers wide, was shrouded in a glowing coma of vaporized material, obscuring its surface and any activity occurring there. Meanwhile, the ion tail, a critical indicator of the comet's interaction with the solar wind, remained invisible to our telescopes. The coma itself was a spectacle of cosmic proportions. This glowing envelope of gas and dust expanded to roughly 150,000 kilometers in diameter, larger than the planet Jupiter. It shimmered with a faint green hue, the result of diatomic carbon C2 molecules fluorescing. Under the intense ultraviolet radiation of the sun, this ethereal glow was a beacon of the comet's activity, yet it also served as a veil, concealing the nucleus and the intricate processes occurring on its surface. The coma's composition was a rich stew of chemicals, including water vapor, carbon dioxide, ammonia, and traces of more complex organic compounds. These molecules, frozen for billions of years in the comet's icy core, were now being liberated. By the sun's heat, creating a transient atmosphere that revealed the comet's primordial origins. Think of it like this. Imagine standing behind a car at night. You can see the tail lights, but the headlights are invisible, pointed forward and blocked by the car's body. Now imagine the car turns, gradually revealing its side. Suddenly you see the glow of the headlights. The lights didn't turn on. They were there all along. You just couldn't see them. Until the angle shifted. This analogy captures the essence of the geometry problem. The comet's features didn't suddenly appear. They were always present. But our fixed vantage point on Earth prevented us from observing them until the alignment of the comet, the sun, and our planet changed. This phenomenon is not unique to 3 Atlas. Throughout history, astronomers have grappled with similar challenges. For example, the rings of Uranus were not discovered until 1977. Despite the planet being known since ancient times because their thin, dark structure was nearly impossible to detect from Earth's perspective. Similarly, the existence of Pluto's largest moon, Charon, was not confirmed until 1978, when advances in telescope technology finally allowed astronomers to resolve the faint object hidden in Pluto's glare. That's what happened with 3 Atlas, as it moved along its trajectory after. Perihelion, the angle between Earth, the Sun, and the comet began to shift. By November 10th, just days after its closest approach to the Sun, the tail was fully visible for the first time. Its intricate structure was laid bare, revealing a complex interplay of forces that had been hidden from view. The tail stretched an astonishing 3.2 million kilometers, longer than the distance from the Earth to the Moon and back. It glowed with a faint blue light. The result of ionized carbon monoxide interacting with ultraviolet radiation from the sun. This revelation was more than just a visual spectacle. It was a window into the comet's behavior during the critical days of perihelion, when solar heating and gravitational forces were at their peak. The tail's structure was not static but dynamic, twisting and writhing like a serpent as it responded to the fluctuating solar wind. This dance of charged particles, was a testament to the delicate balance between the comet's magnetic field and the Sun's powerful influence. The tail's revelation also provided critical insights into the composition of the comet itself. Spectroscopic analysis of the tail's light revealed the presence of heavy ions, such as iron and nickel, which are rarely detected in cometary tails. These elements suggested that the comet's nucleus contained a higher proportion of rocky material than most comets, hinting at a formation process that was distinct from its icy counterparts in the outer solar system. The tail's structure also exhibited signs of disconnection events, where portions of the tail appeared to break off and dissipate into space. These events, known as tail disconnection events, TDEs, are thought to occur when the comet crosses boundaries in the solar wind, such as the heliospheric current sheet, where the magnetic polarity of the Sun's plasma changes. 3 Atlas experienced at least 3 TDEs during its perihelion passage, each one causing the tail to temporarily dim before reforming. Observation. The tail's sudden visibility was a stark reminder of the limitations of Earth-based observation. Even with the most advanced telescopes, our understanding of distant objects is constrained by our fixed perspective. The geometry of the solar system often hides as much as it reveals, leaving astronomers to piece together incomplete data like detectives at a cosmic crime scene. For example, the geometry problem has historically hindered our understanding of solar flares, which often occur on the far side of the Sun, invisible to Earth-based instruments. Similarly, the study of extrasolar planets is complicated by their alignment with their host stars, making it difficult to directly observe their atmospheres or surfaces. The challenges posed by geometry have driven the development of innovative technologies such as the Solar and Heliospheric Observatory, SOHO, which orbits the Sun at a point known as the L1 Lagrange point, providing a continuous view of the Sun's far side. The tail's revelation is just the beginning. Its structure tells a story of extraordinary activity and raises even more questions. The tail was not a single uniform stream of particles, but a braided, twisting ribbon, shaped by the interplay of the comet's magnetic field and the solar wind. This structure suggested that 3 Atlas was not a passive object, but an active participant in its own journey, reacting to the forces around it in ways that were both predictable and surprising. The tail's brightness fluctuated over time, indicating changes in the comet's activity levels that were not fully understood. These fluctuations hinted at a complex internal process, perhaps driven by the sublimation of ices deep within the nucleus, releasing bursts of gas and dust into space. The comet's rotation also played a role, as the uneven heating of its surface caused jets of material to erupt from specific regions, creating localized variations in the tail structure. Speculation. Could these fluctuations be evidence of a hidden mechanism within the comet, one that defies our current understanding of cometary behavior? The tail's structure and behavior were unlike anything seen in previous comets, suggesting that 3 Atlas was not just an ordinary visitor from the outer solar system. Its activity seemed almost deliberate, as if the comet were responding to its environment in ways that were not purely passive. This raised the tantalizing possibility that 3 Atlas was not just a chunk of ice and rock, but a dynamic system, governed by laws of physics that were still beyond our grasp. Some researchers have speculated that the comet's behavior could be influenced by internal processes such as cryovolcanism, where subsurface pockets of liquid water or other volatiles erupt through the comet's crust, driving bursts of activity. Others have proposed that the comet's magnetic field might be unusually strong, interacting with the solar wind in ways that create the observed. Fluctuations in the tail's structure and brightness. Interpretation. The geometry problem underscores the need for a more comprehensive approach to studying comets and other distant objects. Relying solely on Earth-based observation limits our ability to understand the full scope of their behavior. Future missions, such as spacecraft equipped with onboard telescopes or even robotic probes capable of intercepting comets in flight, could provide the multi-angle perspectives needed to overcome the limitations of geometry. Such missions would not only reveal hidden features like 3 Atlas's tail, but also help unravel the mysteries of cometary activity, shedding light on the processes that shape these enigmatic objects. For example, the European Space Agency's Rosetta mission, which rendezvoused with Comet 67P Churyumov-Gerasimenko in 2014, provided unprecedented insights into the comet's structure, composition, and behavior through a combination of remote sensing and in situ measurements. Similarly, NASA's upcoming Comet Rendezvous, Sample Acquisition, Investigation and Return, Corsair mission, aims to collect samples from a comet's nucleus and return them to Earth for detailed analysis. Known, the tail was there all along, hidden by viewing geometry. Its structure and behavior suggest complex internal activity within the comet. Unknown. What other changes might we have missed during those critical days? Could the tail's fluctuations be evidence of an unknown mechanism within 3 Atlas? How can future missions overcome the limitations of Earth-based observation to reveal the full story of comets like 3 Atlas? The answers to these questions may lie in the development of new technologies and mission concepts, such as constellations of small satellites capable of tracking comets from multiple angles simultaneously. Such innovations could revolutionize our understanding of these celestial wanderers and their role in the solar system's history. Part 3. The Tail That Shouldn't Exist. What if the most extraordinary structures in the universe are the ones we can't see? The universe, vast and unknowable, often reveals its mysteries through the subtle and the invisible. The tail of 3 Atlas, a comet that has puzzled astronomers since its discovery, is one such enigma. It defies conventional understanding, challenging our assumptions about the behavior of celestial bodies and the forces that shape them. This comet, officially designated C2023A3, was first observed in early 2023, its tail already exhibiting unusual characteristics that set it apart from other comets. Its orbital path suggests it originated in the Oort cloud, a distant region of icy bodies that lies far beyond the outer planets. This distant origin means 3 Atlas has spent billions of years in the deep freeze of space, preserving materials from the early solar system. The November 10th images from the Virtual Telescope Project are more than just stunning photographs. They're scientific documents, encoding the physical processes occurring within and around 3 Atlas. The tail's complexity is unprecedented. Multiple streamers extend from the nucleus, each potentially representing a distinct outgassing source or interaction with the solar wind. The tail isn't straight, it curves gently, responding to the balance between solar wind pressure and the magnetic field embedded in the wind. This curvature is not a random phenomenon, but a precise interplay of forces, a dance between the comet and the sun that has been ongoing for millennia. The tail stretches over 10 million kilometers, longer than the distance from Earth to Venus at its closest approach, yet its delicate structure is shaped by forces that operate on scales as small as individual molecules. Observation. The tail's structure suggests either complex outgassing patterns from the nucleus or interaction with structured solar wind, or both. The solar wind, a stream of charged particles ejected from the sun, exerts a constant pressure on the comet's tail. This pressure, combined with the magnetic field carried by the wind, shapes the tail into its distinctive form. The tail's curvature could indicate variations in the solar wind's intensity or direction, or it could reflect changes. In the comet's own outgassing activity, the multiple streamers further complicate the picture, suggesting that the comet's nucleus is not uniform, but contains distinct regions of activity. Some of these streamers appear to twist slightly, hinting at the presence of rotating jets of gas or the influence of the comet's own weak magnetic field. But here's where things get strange. Cometary ion tails are typically straightforward, narrow streams of ionized gas pointing away from the sun. 3 Atlas's tail is anything but straightforward. Its multiple streamers and curved features suggest either unusual outgassing patterns or interaction with a structured solar wind, or both. The tail's behavior is so unusual that it has forced astronomers to re-evaluate their models of cometary activity. In some images, the tail appears to split into finer filaments, a phenomenon rarely observed in other comets. These filaments may be the result of instabilities in the solar wind or the fragmentation of the outgassing streams as they interact with the surrounding plasma. Speculation: could the tail's complexity hint at an unusual composition or internal structure within the comet? The tail's blue-green glow is another clue. It comes from ionized molecules, carbon monoxide, water, and other volatiles excited by solar ultraviolet radiation. The color itself is a diagnostic, telling us we're seeing ionized gas, not reflected sunlight from dust. This glow is a direct result of the comet's interaction with the sun, a visible manifestation of the energy exchange between the two bodies. The intensity and distribution of the glow could provide insights into the composition of the comet's nucleus, revealing the presence of specific molecules and their relative abundances. For example, the brightness of the carbon monoxide emission suggests that this molecule is particularly abundant in 3 Atlas, which could imply that the comet formed in a region of the solar system where carbon monoxide was more plentiful. Known: the tail's complexity indicates intense activity and significant outgassing. Unknown: what does this activity tell us about the comet's composition and origin? The tail structure is a puzzle, but it is not the only one. The comet's nucleus, hidden beneath the glowing tail, holds its own secrets. The outgassing activity that produces the tail is driven by the sublimation of ices within the nucleus, a process that releases volatile gases into space. The rate and composition of this outgassing depend on the comet's internal structure, temperature, and exposure to solar radiation. By studying the tail, astronomers hope to unravel the mysteries of the nucleus and understand the forces that have shaped 3 Atlas over its long journey through the solar system. Recent observations suggest that the nucleus is rotating more rapidly than expected, which could explain the multiple streamers in the tail. This rapid rotation may also be causing internal stresses within the nucleus, potentially leading to fractures or even breakup in the future. The tail is just the beginning. Its structure hints at even more profound changes occurring within the comet itself. These changes could include shifts in the nucleus's rotation, internal heating, or the release of trapped gases from deep within the comet's core. Each of these processes would leave its mark on the tail, altering its shape, brightness, or composition. By monitoring these changes, astronomers can piece together the story of 3 Atlas, a story that spans billions of years and untold distances. For instance, the tail's brightness has fluctuated over time, suggesting that the comet's activity is not constant, but varies in response to internal or external factors. These fluctuations could be caused by changes in the comet's orientation relative to the Sun, or by the release of pockets of gas trapped within the nucleus. One of the most intriguing possibilities is that the tail's complexity reflects an unusual composition within the comet's nucleus. Comets are often described as dirty snowballs composed of a mixture of ices and dust. However, the exact composition of these ices can vary widely, depending on the conditions under which the comet formed. 3 Atlas's tail may be hinting at the presence of exotic ices or organic compounds, materials that could provide clues to the comet's origin and the environment in which it formed. Spectroscopic analysis of the tail's emission has detected traces of complex organic molecules such as methanol and formaldehyde, which are rarely seen in comets. These molecules could indicate that 3 Atlas formed in a region rich in organic material, possibly near the outer edges of the solar system. Another possibility is that the tail's structure is influenced by the comet's interaction with the solar wind. The solar wind is not a uniform stream, but a complex and dynamic phenomenon, shaped by the Sun's magnetic field and the rotation of its corona. Variations in the solar wind's intensity or direction could produce the multiple streamers and curves observed in 3 Atlas's tail. By studying these features, astronomers can learn more about the solar wind itself, as well as its effects on comets and other celestial bodies. For example, the tail's curvature seems to correlate with periods of increased solar activity, such as solar flares or coronal mass ejections. This correlation suggests that the solar wind's variability is directly influencing the tail's shape and behavior. The tail's blue-green glow is not just a visual spectacle, but a window into the comet's chemical makeup. The glow is produced by the excitation of specific molecules, such as carbon monoxide and water, by solar ultraviolet radiation. By analyzing the wavelengths of light emitted by the tail, astronomers can identify the molecules present and determine their relative abundances. This information in turn provides insights into the comet's formation and evolution, as well as the conditions in the early solar system. The tail's spectrum also reveals the presence of rare isotopes, such as deuterium, which could indicate that 3 Atlas formed in a colder region of the solar system where heavy isotopes were more abundant. The tail's complexity also raises questions about the comet's internal structure. Comets are not solid objects, but porous aggregates of ice and dust, held together by gravity and the weak forces between molecules. The outgassing activity that produces the tail could be influenced by the distribution of these materials within the nucleus, as well as the presence of cracks or fissures that allow gases to escape more easily. By studying the tail's structure and behavior, astronomers can infer the properties of the nucleus and the processes that shape it. High-resolution images of the tail show fine details such as small-scale jets and clumps of material, which may correspond to specific features on the nucleus. These features could include active vents, craters, or regions of exposed ice, all of which contribute to the tail's complexity. The tail's unusual features have sparked intense debate among astronomers. Some argue that the tail's complexity is a sign of recent changes within the comet, such as a sudden increase in outgassing activity or a shift in the nucleus's rotation. Others suggest that the tail's structure reflects long-term processes, such as the gradual erosion of the nucleus by solar radiation or the accumulation of dust and debris over time. Still others propose that the tail's behavior is influenced by external factors, such as variations in the solar wind or the gravitational influence of nearby planets. For example, the tail's orientation seems to shift slightly as the comet passes through regions of denser solar wind, indicating that the wind's pressure is directly shaping the tail's structure. Despite the many unknowns, one thing is clear. 3 Atlas is a comet unlike any other. Its tail, a luminous ribbon of ionized gas, is a testament to the comet's dynamic nature and the forces that shape it. By studying this remarkable object, astronomers hope to unravel the mysteries of cometary activity, solar-wind interaction, and the origins of the solar system itself. The tail that shouldn't exist is not just a curiosity, but a gateway to understanding the universe in all its complexity and wonder. As 3 Atlas continues its journey through the solar system, it will undoubtedly reveal more of its secrets, challenging our understanding of comets and the forces that govern their behavior. Part 4. The Brightness Surge. What if the brightest objects in the universe are the ones hiding the darkest secrets? 3 Atlas didn't just change physically, it brightened far more rapidly than models predicted as it approached perihelion. Most comets brighten with solar distance raised to the power of 3 or 4, but 3 Atlas scaled at 7.5, a dramatic surge that defied convention. At its peak, it outshone comparable comets by several orders of magnitude, glowing like a cosmic beacon. While typical comets might brighten by a factor of 100, 3 Atlas brightened by over 10,000 hours, becoming visible even in small amateur telescopes. Its greenish hue, caused by the emission of diatomic carbon, C2 molecules, painted a stark contrast against the black canvas of space, a spectacle that captivated both professional astronomers and stargazers worldwide. This brightness surge wasn't just a curiosity, it was a puzzle demanding explanation. Astronomers turned their instruments toward 3 Atlas, capturing its behavior in unprecedented detail. The Hubble Space Telescope, Keck Telescope, and the Very Large Telescope tracked the comet's every move. Spectroscopic data revealed a dynamic and brighter than expected coma, with jets of material erupting from the nucleus, creating intricate shifting patterns. These jets, some as wide as 10,000 kilometers, spewed out dust and gas at velocities exceeding 500 meters per second, generating a chaotic, ever-changing environment. The coma itself expanded to over 80,000 kilometers in diameter, enveloping the comet in a hazy, glowing shroud. Interpretation. The steep brightness scaling suggests an unusually volatile composition, or a highly porous structure maximizing gas production efficiency. 3 Atlas may have had a porosity of 80%, making it more like a cosmic sponge than a solid rock. Alternatively, it could have contained extremely volatile ices like carbon monoxide or carbon dioxide, which sublimate at lower temperatures than water ice. Buried deep within the nucleus, these ices might have released a torrent of gas and dust as the comet neared the sun. Models suggest that the nucleus could have lost up to 1% of its mass during this period, ejecting billions of kilograms of material into space. One striking observation was the comet's behavior as it crossed the frost line, where water ice remains stable. Beyond this line, icy bodies retain volatile materials. Inside it, they sublimate rapidly. 3 Atlas crossed this boundary at about 5 AU from the Sun, and its brightness surged exponentially, suggesting its nucleus was packed with volatile materials waiting to escape. This nucleus, just a few kilometers in diameter, was a time capsule from the early solar system. preserving materials unchanged for billions of years. Its surface, darkened by organic compounds and primordial dust, reflected less than 4% of the sunlight that hit it, making the brightness surge even more dramatic. But the brightness surge wasn't the only anomaly. Near perihelion, 3 Atlas's light became distinctly bluer, indicating gas emission-dominated light production. This blue shift was pronounced in the ultraviolet spectrum, where emissions from molecules like CN and OH became intense. These signatures suggest the comet was releasing complex organic compounds, hinting at its potential role in delivering organic materials to the early Earth. The ultraviolet emissions were so strong that they temporarily saturated the sensors of some observing spacecraft, requiring adjustments to continue monitoring. Speculation. Could this intense activity hint at a pristine, highly volatile nucleus? Experiencing its first close approach to a star, if 3 Atlas had been dormant for millennia, its ices would have remained untouched by solar radiation, preserving their original composition. Without an insulating crust, it would have been free to release stored volatiles in a spectacular display. By contrast, Halley's Comet, which has made dozens of trips through the inner solar system, has a dark crust that limits its brightness. Halley's brightness. Peaking at magnitude 0.2, pales in comparison to 3 Atlas's dazzling 3 magnitude at its brightest. The implications of a pristine nucleus are profound. 3 Atlas could offer astronomers a rare opportunity to study a comet in its original state, providing a snapshot of the early solar system. Its brightness surge and gas emission could reveal the chemistry and structure of the primordial solar nebula. The nucleus, if studied in detail, might contain isotopic ratios of elements like hydrogen and oxygen, offering clues about the temperature and pressure conditions during the solar system's formation. However, some astronomers point to 3 Atlas's unusual orbit as evidence of a more complex history. Its highly eccentric and inclined orbit suggests it may have been perturbed by an unknown force. One theory proposes that 3 Atlas is a fragment of a larger comet that broke apart during a close encounter with a planet or another large body. This collision could have exposed fresh, volatile-rich material, leading to its dramatic brightening. If correct, 3 Atlas may not be a time capsule but a recent creation born from catastrophic breakup. Simulations indicate that such an event could have occurred as recently as 500 years ago, making 3 Atlas a cosmic newcomer. Known, 3 Atlas brightened dramatically and exhibited intense gas emission near perihelion. Its light became distinctly bluer, indicating a shift toward gas-dominated emission. Unknown, what combination of composition and structure could explain this behavior? Was 3 Atlas truly experiencing its first close approach to the Sun, or was something else at play? The brightness surge and spectral shift hint at profound changes within the comet itself. As 3 Atlas continued its journey, its tail underwent further transformations. The dust component fragmented into distinct streams following specific trajectories that suggested discrete shedding events rather than continuous release. Each event coincided with a minor brightness spike, as if the comet were releasing pockets of trapped gas and dust in bursts. These bursts, some lasting mere hours, created temporary filament-like structures in the tail, glowing faintly against the backdrop of the solar system. High-resolution images revealed that the streams were not uniform in composition. Some were rich in dust, while others were dominated by gas, particularly ionized species like CO+ and H2O+. This heterogeneity implies a non-homogeneous nucleus composed of distinct regions with varying compositions, possibly formed from the accretion of smaller, chemically diverse bodies, the dust grains ranging from micrometers to centimeters. In size, scattered sunlight in intricate patterns, creating a mesmerizing display that astronomers compared to a cosmic aurora. Interpretation: the fragmentation of the tail and discrete brightness spikes suggest localized outbursts triggered by the sublimation of volatile pockets within the nucleus or structural failures due to internal pressures. These outbursts could have been caused by the rapid sublimation of buried ices, creating cavities within the nucleus and leading to sudden collapses that released large amounts of gas and dust. The energy released during these events was equivalent to detonating thousands of tons of TNT, reshaping the comet's surface and ejecting material into space. The implications are profound. If 3 Atlas is a pristine comet, it offers a glimpse into the early solar system, reflecting the conditions during planet formation, its composition and structure. Could provide clues about the building blocks of our cosmic neighborhood. However, if its behavior results from recent processes like a collision, it raises questions about the stability and evolution of small bodies in the outer solar system. The comet's future is equally uncertain. Its volatile-rich nucleus may continue to fragment, eventually breaking apart entirely or stabilizing into a dormant state once more. Speculation: could 3 Atlas be a remnant of a larger disrupted body, or is it a primordial relic? Its unusual brightness and activity hint at a complex history spanning billions of years. As astronomers study this enigmatic object, they hope to unravel its secrets and shed light on cometary behavior and the origins of our cosmic home. The comet's trajectory will carry it back to the outer solar system, where it will remain for millennia before returning, if it survives its current journey intact. One exciting possibility is that 3 Atlas could become a target for future spacecraft missions. If its unusual behavior continues, it may be prioritized for exploration, offering scientists an opportunity to study a comet in unprecedented detail. Proposed missions could collect samples, analyze its composition, and even return material to Earth. Such a mission would advance our understanding of 3 Atlas and provide insights into the nature of comets and their role in the evolution of the solar system. Already, space agencies are discussing the feasibility of launching a probe to rendezvous with 3 Atlas during its next approach, though such a mission would require years of planning and technological innovation. For now, 3 Atlas remains a mystery, its brightness, surge, and anomalies defying easy explanation. But with each observation, astronomers are piecing together its story, one that spans the history of the solar system and hints at the profound connections between comets, planets, and the origins of life. As the comet continues its journey, it carries the secrets of the past and the promise of discoveries yet to come. Its tail, stretching millions of kilometers behind it, trails like a cosmic question mark, inviting humanity to unravel the enigmas of the universe one comet at a time. Part 5. The Acceleration Anomaly. What if the most extraordinary forces in the universe are the ones we can't see? As astronomers tracked 3 Atlas's position before and after perihelion, they noticed something strange. The comet wasn't where it should have been. Its trajectory deviated slightly from predictions based purely on gravitational forces. This discrepancy is known as non-gravitational acceleration, forces acting on the comet's nucleus other than gravity. The deviation was subtle but unmistakable, a whisper of defiance against the rigid laws of celestial mechanics. Over the course of weeks, the comet drifted off its predicted path by a distance equivalent to thousands of kilometers, an aberration that grew more pronounced as it approached the Sun. At its closest approach, the deviation measured approximately 12,000 kilometers, a distance greater than the diameter of Earth. This unexpected detour sparked a flurry of activity among researchers who scrambled to explain the rogue behavior of this icy wanderer. Observation: non-gravitational acceleration is typically caused by outgassing, gas jetting away from the nucleus, pushing it in the opposite direction. This phenomenon is well documented in comets, but 3 Atlas seem to be breaking the rules. The intensity and direction of the outgassing were far beyond what scientists had observed in similar comets. For example, Comet 67P Churyumov-Gerasimenko, studied extensively by the Rosetta mission, exhibited outgassing that produced non-gravitational acceleration, but at a much smaller scale. 3 Atlas, on the other hand, seemed to be expelling material with unprecedented force. Observations from the Hubble Space Telescope and ground-based facilities like the Keck Observatory in Hawaii revealed jets of carbon dioxide and water vapor erupting from the comet's surface at velocities exceeding 1 kilometer per second. These jets were so powerful that they created a faint, glowing halo around the comet, visible in infrared images as a diffuse cloud of ejected material. The outgassing was not uniform. Imaging from ground-based observatories revealed jets of gas and dust erupting from specific regions of the comet's nucleus, creating a chaotic, asymmetrical pattern. These jets, glowing faintly in the ultraviolet spectrum, acted like tiny rocket engines nudging the comet off its expected course. The radial component of the acceleration suggested that the comet was being pushed directly away from the Sun, likely due to intense solar heating vaporizing ices deep within its core. The transverse component, however, hinted at a more complex process, perhaps a rotational wobble caused by uneven outgassing or even structural changes within the nucleus itself. Spectroscopic analysis of the outgassing revealed the presence of volatile compounds such as methane, ammonia, and even traces of complex organic molecules, suggesting that the comet was not only losing mass but also releasing primordial materials preserved since the early days of the solar system. But the magnitude of this acceleration was surprising. Using the rocket equation, researchers estimated that producing this acceleration would require the comet to lose 10⁻⁻13% of its total mass over the course of a month. To put this into perspective, a typical comet might lose less than 1% of its mass during a single perihelion passage. 3 Atlas, however, seemed to be shedding material at a rate that defied conventional models. If accurate, this mass loss would imply that the comet was undergoing a catastrophic event, one that could dramatically alter its structure and composition. The total mass ejected during this period was estimated to be between 100 million and 1 billion kilograms, enough to form a small asteroid. This extreme outgassing also left a visible trail of debris along the comet's path, stretching over 500,000 kilometers and reflecting sunlight like a faint, ghostly ribbon in the sky. Speculation: could 3 Atlas have lost such a significant fraction of its mass? Or are the calculations overestimating the mass loss? The answer to this question could redefine our understanding of cometary behavior. One possibility is that the comet's nucleus is far less dense than expected, allowing it to lose mass more easily. Alternatively, the outgassing might be driven by unusual chemical processes, such as the sublimation of exotic ices or the release of trapped gases from deep within the comet's interior. Some researchers have proposed that 3 Atlas may contain pockets of highly volatile materials, such as solid nitrogen or carbon monoxide, which could undergo explosive sublimation when exposed to solar heating. This hypothesis is supported by the detection of unusually high concentrations of these compounds in the comet's coma, the diffuse cloud of gas and dust surrounding the nucleus. Another theory suggests that 3 Atlas might have experienced a sudden fracture or collapse of its nucleus, releasing a massive burst of material in a short period. Such an event could explain the rapid acceleration and the extreme brightness surge observed earlier. However, this scenario raises even more questions. What could cause such a dramatic failure? Was it a result of internal stresses, solar heating, or perhaps an unseen collision with another celestial object? Some models suggest that the comet's nucleus may have been weakened by repeated passages through the inner solar system, gradually destabilizing its structure until it reached a critical point. Alternatively, the comet may have collided with a previously undetected object, such as a small asteroid or another comet fragment, triggering a catastrophic release of energy and material. Known: 3 Atlas experienced non-gravitational acceleration during perihelion. The deviation in its trajectory was measurable and consistent with outgassing, though the exact mechanisms remain unknown. How much mass did the comet actually lose? Was the mass loss uniform, or did it occur in sudden violent bursts? What role did the comet's internal structure play in this process? The acceleration anomaly is just the beginning. It points to even more profound questions about the comet's behavior and origin. 3 Atlas is not just a curiosity, it is a puzzle piece in the larger story of the solar system. Its unusual acceleration challenges our understanding of how comets evolve and interact with the Sun. If the comet's behavior is a result of unique internal processes, it could offer insights into the composition and history of the outer solar system, where such icy bodies are believed to have formed billions of years ago. The study of 3 Atlas could also shed light on the role of comets in delivering water, organic compounds, and other essential materials to the early Earth, potentially seeding the conditions for life. As scientists continue to study 3 Atlas, the comet's journey becomes a microcosm of the cosmic drama that has unfolded since the birth of the solar system. The forces that shaped it, the materials that compose it, and the mysteries it holds may one day rewrite the story of our celestial neighborhood. For now, the acceleration anomaly remains a tantalizing clue, a celestial riddle waiting to be solved. Future missions, such as the proposed Comet interceptor by the European Space Agency, could one day rendezvous with 3 Atlas or similar objects, providing up-close observations and samples that could unlock the secrets of these enigmatic travelers. Until then, astronomers will continue to watch, measure and wonder at the strange and unpredictable journey of 3 Atlas, a comet that defies explanation and challenges our place in the cosmos. Part 6. The Mass Loss Paradox. What if the most extraordinary transformations in the universe are the ones we can't see? The cosmos is filled with mysteries that defy easy explanation, but few are as perplexing as the case of Comet 332p Ikea Murakami, also known as 332p. This comet, discovered in November 2010, has become a focal point of scientific inquiry due to its perplexing behavior. At the heart of the mystery lies an astonishing revelation: the estimated mass loss of 13% is staggering. To put this into perspective, imagine a comet with a nucleus roughly 1.5 kilometers in diameter. A loss of 13% of its mass would equate to shedding hundreds of millions of tons of material, enough to fill a small mountain range. Yet here lies the paradox. Some observers claim the comet looks largely unchanged in images captured over time. How can such a dramatic mass loss occur without obvious evidence in the visual record? The answer lies in the nature of mass loss itself. When a comet loses mass, it's primarily through gas sublimating from the nucleus, ice turning directly to gas and escaping into space. This process is not unique to 332P. It's a common characteristic of comets as they approach the Sun. However, what sets 332P apart is the sheer scale of its mass loss. The sublimating gas, primarily composed of water vapor, carbon dioxide, and other volatile compounds, is invisible to optical telescopes once it leaves the immediate vicinity of the nucleus. It disperses rapidly into the vacuum of space, becoming too diffuse to image directly. This is further complicated by the comet's distance from Earth, which can exceed 100 million kilometers, making even the smallest details difficult to resolve. Observation. Dust, which is visible, also disperses quickly. The particles ranging from micron-sized grains to pebble-sized. Fragments are pushed away by solar radiation pressure and aerodynamic drag from the escaping gas. Over time, this dust spreads into a large, tenuous cloud that grows dimmer with distance, blending into the darkness of space. Astronomers have noted that 332P's dust tail, while clearly present, does not appear significantly denser or more extensive than those of other comets with lower estimated mass loss rates. This has led to questions about weather. The mass loss is occurring in a way that defies conventional models. For example, the dust tail of Comet 67P Churyumov-Gerasimenko, as observed by the Rosetta mission, extended up to 1,500 kilometers from the nucleus. Yet 332P's tail does not exhibit such pronounced features despite its higher mass loss rate. To better understand this phenomenon, consider the comet's behavior during its closest approach to the Sun, known as perihelion. In January 2016, 332P reached perihelion at a distance of approximately 1.6 astronomical units, AUs from the Sun. During this period, the comet's activity peaked, with intense outgassing and dust production. However, even at this critical phase, the comet's appearance in images remained relatively stable. This stability is not due to a lack of activity, but rather a testament to the efficiency with which the comet sheds material, the escaping gas and dust create. A dynamic, ever-changing environment around the nucleus, but the nucleus itself may remain surprisingly intact. This behavior contrasts with comets like Ison, which disintegrated entirely during its perihelion approach in 2013, highlighting the unique resilience of 332P's structure. Speculation. Could the lack of obvious structural changes in images mean the mass loss was overestimated? Or are our observational limits preventing us from detecting changes that actually occurred? The latter seems more likely. The comet's nucleus may have undergone significant internal restructuring, with subsurface ice pockets collapsing and redistributing mass in ways that are not immediately visible. Alternatively, the mass loss could be concentrated in specific regions of the nucleus, creating localized features that are too small to detect with current technology. This raises the possibility that 332P's mass loss is not uniform, but rather a product of complex, uneven processes. For instance, the comet's rotation period of approximately 7.4 hours could influence how mass loss is distributed, with certain regions experiencing more intense outgassing due to prolonged exposure to solar radiation. Known, 332p definitely experienced non-gravitational acceleration and lost mass through outgassing. This acceleration, measured at 1.4 × 10^7 km/s2, is a clear indicator of the comet's dynamic behavior. The non-gravitational forces at play are likely the result of intense outgassing, which propels the comet forward like a natural rocket engine. This phenomenon has been observed in other comets, but 332p's case is notable for its magnitude and consistency. For comparison, the non-gravitational acceleration of Halley's comet is roughly 3 times lower, at 4.5 × 10^8 km/s2, despite Halley being a much larger and more active comet. Unknown how much mass was actually lost. The exact figure remains elusive as current models struggle to reconcile the observed mass loss with the comet's apparent stability. Some researchers estimate that the total mass loss could exceed 10^10 kilograms, though this figure is highly uncertain. Future observations, particularly those using advanced infrared and ultraviolet instruments, may provide clearer answers. The upcoming James Webb Space Telescope, with its unprecedented sensitivity in the infrared spectrum, could revolutionize our understanding of 332p's mass loss by detecting faint signatures of gas and dust that are currently beyond our reach. The mass loss paradox is just the beginning. It points to even more profound questions about the comet's behavior and origin. For instance, how does 332p maintain its structural integrity despite such dramatic mass loss? What internal processes are driving this behavior, and are they unique to this comet or a common feature of cometary evolution? As scientists delve deeper into these questions, they are not only unraveling the mysteries of 332p, but also gaining insights into the broader dynamics of the solar system. The comet's behavior may even offer clues about the early solar system's environment, where collisions and fragmentation events were far more common. One intriguing theory suggests that 332p's behavior is the result of a recent fragmentation event. Comets are notoriously fragile, and collisions or tidal forces from planets like Jupiter can cause them to break apart. If 332p experienced such an event in the past, the resulting fragments could still be loosely bound together, giving the appearance of a single intact nucleus while allowing for significant mass loss through sublimation. This theory is supported by the presence of multiple fragments observed in the comet's vicinity, though their exact relationship to the main nucleus remains unclear. For example, during its 2016 perihelion, at least 16 fragments were detected within 332p's coma, suggesting a complex and ongoing fragmentation process. Another possibility is that 332p's nucleus is unusually porous, with a sponge-like structure that allows gas to escape more efficiently than in other comets. This porosity could be the result of prolonged exposure to solar radiation, which gradually erodes the nucleus's surface and creates a network of internal cavities. If true, this would explain why the comet appears stable despite losing so much mass. The nucleus itself is designed to withstand such losses. High-resolution radar observations from Earth-based telescopes, such as the Arecibo Observatory, could help test this hypothesis. By mapping the nucleus's internal structure and measuring its density, regardless of the explanation, 332p's behavior challenges our understanding of cometary dynamics. As researchers continue to study this enigmatic object, they are not only uncovering the secrets of a single comet, but also shedding light on the fundamental processes that shape our solar system. The mass loss paradox, far from being a dead end, is a gateway to a deeper understanding of the cosmos. It invites us to question our assumptions, refine our models, and push the boundaries of what we know about the universe. In doing so, 332p becomes more than just a comet. It becomes a window into the mysteries of creation and destruction that define the cosmos itself. Part 7. The Spacecraft Encounter. What if the most extraordinary discoveries in the universe are the ones we never planned for? In the vast, unpredictable theatre of space, serendipity often plays a leading role. The cosmos is a stage where chance alignments and unexpected encounters can transform our understanding of the universe. For scientists studying the Comet 3 Atlas, such an opportunity may have presented itself in the most unexpected way. As researchers tracked 3 Atlas through perihelion, its closest approach to the Sun, they realized something extraordinary. 2 spacecraft, ESA's Hera and NASA's Europa Clipper, might have flown directly through the comet's ion tail. This tail, a sprawling trail of charged particles and dust, stretches millions of kilometers into space, a ghostly apparition visible only through the eyes of sensitive instruments. If the spacecraft did indeed cross this ethereal path, they're on board. Systems could have recorded data that would provide unprecedented insights into the comet's composition and outgassing behavior. The possibility is both exhilarating and humbling, a reminder of how much of the cosmos remains uncharted territory. The spacecraft in question are no ordinary probes. Hera, part of ESA's ambitious Asteroid Impact and Deflection Assessment (AIDA) mission, is designed to study the aftermath of NASA's DART impact on the asteroid Dimorphos. It carries a suite of instruments including magnetometers, plasma detectors and dust counters, all finely tuned to measure the subtle fluctuations of its environment. Hera's journey to Dimorphos spans over 11 million kilometers, a trek that requires precision engineering to ensure its instruments remain functional in the harsh conditions of space. Similarly, NASA's Europa Clipper, en route to Jupiter's icy moon Europa, is equipped with advanced sensors to probe the moon's subsurface ocean and the complex plasma environment around Jupiter. Europa Clipper's voyage covers a staggering 2.5 billion kilometers, traversing the solar system with cutting-edge technology designed to withstand the intense radiation belts of Jupiter. Both spacecraft are essentially flying laboratories, capable of detecting even the faintest whispers of cometary material. Observation: the spacecraft carry instruments sensitive to environmental conditions, including magnetometers, plasma detectors, and dust counters. Hera's magnetometer, for instance, can measure magnetic field variations as subtle as 0.1 nanotesla, while Europa Clipper's plasma instrument for magnetic sounding, PIMs, can detect ion densities as low as 0.01 particles per cubic centimeter. These instruments are so precise that they could theoretically detect the presence of cometry, ions and dust, even if the spacecraft passed through the outermost fringes of 3 Atlas's ion tail. The tail itself is a dynamic structure shaped by the solar wind's relentless pressure, which accelerates ions and dust particles to speeds exceeding 400 kilometers per second. This interaction creates a tenuous but detectable trail, stretching over 10 million kilometers into space. Speculation: could these instruments have detected telltale signatures of cometary material? If so, the data could revolutionize our understanding of comets. For example, the composition of the ions in the tail could reveal the chemical makeup of the comet's nucleus, shedding light on the primordial materials that formed it billions of years ago. Comets like 3 Atlas are believed to be time capsules from the early solar system, preserving the building blocks of planets and moons. Similarly, variations in the magnetic field could indicate the presence of electric currents generated by the interaction between the comet's plasma and the solar wind, providing clues about the comet's dynamic behavior. These currents can reach intensities of up to 100 nanoamperes per square meter, generating subtle but measurable disturbances in the magnetic field. The potential spacecraft encounter adds an entirely new dimension to the investigation. It's a reminder that discovery doesn't always come from carefully planned observations. Sometimes it comes from being alert to opportunities and recognizing connections that weren't obvious until someone took the time to calculate the orbital geometry. This is not the first time such a serendipitous event has occurred. In 2007, for instance, NASA's Cassini spacecraft inadvertently flew through the plume of Saturn's moon Enceladus, revealing the presence of a subsurface ocean and revolutionizing our understanding of the icy moon. The plume, ejecting water vapor and ice particles at speeds of up to 400 meters per second, provided invaluable data about the moon's internal processes. Similarly, in 2018, the ESA JAXA Bepi-Colombo mission captured unexpected observations of Mercury's magnetosphere during a flyby, offering new insights into the planet's interaction with the solar wind. These examples underscore the importance of being prepared to seize unplanned opportunities in space exploration. The orbital calculations that suggest a tail crossing are complex but compelling. 3 Atlas's ion tail stretched out by the solar wind extends over 10 million kilometers in length, a vast yet tenuous structure. When researchers analyzed the trajectories of Hera and Europa Clipper, they found that both spacecraft passed within this region at approximately the right time. The geometry is not perfect. The spacecraft were not aimed directly at the comet, but the margins of error are small enough to make the possibility tantalizing. If confirmed, this encounter would be one of the closest unplanned flybys of a comet in history. The last such event occurred in 2013, when NASA's Deep Impact spacecraft observed Comet ISON from a distance of 9.5 million kilometers, providing critical data about its composition and behavior. Known, the geometry suggests a tail crossing might have occurred. The timing aligns. Hera passed within 8.5 million kilometers of 3 Atlas on May 12, 2030, while Europa Clipper came within 9.3 million kilometers on June 4, 2030. Both distances fall well within the estimated length of the comet's iron tail. The data collected during these flybys includes over 20 gigabytes of magnetic field measurements, plasma readings, and dust counts, all of which are being meticulously analyzed. Unknown. Did the spacecraft actually traverse the tail? And if so, did their instruments detect diagnostic signatures? The data is still being analyzed, and the teams are cautiously optimistic. The process involves comparing the spacecraft's readings with models of cometary tails, a painstaking effort that could take months to complete. The spacecraft encounter is just the beginning. It points to even more profound questions about the comet's behavior and origin. For instance, if the spacecraft did detect cometary material, it could help scientists estimate the mass loss rate of 3 Atlas with unprecedented accuracy. This, in turn, could shed light on the mechanisms driving the comet's outgassing and the processes shaping its evolution. Additionally, the chemical composition of the detected material could provide clues about the comet's formation, offering a glimpse into the early solar system. Comets are thought to have played a crucial role in delivering water and organic compounds to Earth, potentially seeding the conditions for life. Understanding their composition could help us unravel the mysteries of our planet's origins. The stakes are high and the possibilities are exhilarating. If the spacecraft did indeed cross paths with 3 Atlas, the data they collected could rewrite our understanding of comets and their role in the solar system. But even if the encounter turns out to be a near miss, the story is far from over. The pursuit of knowledge in space is a journey of patience, persistence, and endless curiosity. As researchers continue to analyze the data and refine their models, the comet's secrets slowly come into focus, one discovery at a time. The journey of exploration is not just about the destinations we plan for, but also the unexpected encounters that challenge our assumptions and expand our horizons. Part 8. The Origin Mystery. What if the most extraordinary objects in the universe are the ones that tell us where they came from? 3 Atlas is more than just a comet. It's a physical sample from interstellar space, carrying information about its birthplace and journey encoded in its composition, structure, and behavior. Its intense activity near perihelion suggests it's rich in volatile ices that sublimate readily, pointing to formation in a cold environment analogous to the outer regions of our solar system. As it approached the sun, it released a brilliant coma of gas and dust, a spectacle that hinted at its origins. The coma's chemical signature, rich in water ice, carbon monoxide, and other volatile compounds, mirrored the compositions of objects found in the Kuiper Belt and Oort Cloud, the icy reservoirs at the edge of our own solar system. The coma stretched over 1 million kilometers, glowing faintly under. The sun's influence, a delicate, ephemeral halo that offered astronomers a fleeting glimpse into its distant past. Its tail, stretching millions of kilometers, shimmered with ionized gases that interacted with the solar wind, creating a dynamic display of plasma physics in action. Imagine the scene. 3 Atlas drifting through the abyss of interstellar space for millions, perhaps billions of years, its surface untouched by sunlight for eons, preserved the pristine conditions of its birthplace. Then, as it entered our solar system, the faint but relentless tug of the sun's gravity began to warm its icy core. The once dormant object awakened, releasing plumes of gas and dust that had been locked away since its formation. This awakening provided astronomers with a rare opportunity to study a time capsule from another star system, one that had travelled unimaginable distances to reach us. Its journey through the galaxy likely took it through regions of varying radiation and gravitational intensity, each leaving subtle imprints on its composition and structure. Every molecule, every grain of dust, held stories of supernova explosions, stellar winds, and the quiet hum of cosmic background radiation. Observation. Polarization data suggests a surface composition similar to trans-Neptunian objects like Pluto and Eris, supporting the idea of formation in a cold, distant region. The polarization measurements, captured during its closest approach to Earth, revealed a surface rich in methane and nitrogen ices, much like the dwarf planets of the outer solar system. These ices, which form only in extremely cold environments, further strengthen the hypothesis that 3 Atlas originated in a region far from its parent star. The reflectivity of its surface, only about 4% of the sunlight it received, indicated a dark, ancient crust, likely the result of prolonged exposure to cosmic rays and micrometeoroid impact during its interstellar voyage. Its spectral analysis showed traces of complex organic molecules including polycyclic aromatic hydrocarbons, PAHs, which are thought to be precursors to life. Speculation. Could 3 Atlas have formed in a planetary system with giant planets capable of scattering objects to large distances? The presence of giant planets like Jupiter and Saturn in our solar system could have played a crucial role in its origin story. These massive worlds, with their powerful gravitational fields, are known to eject smaller bodies from their orbits, sending them on interstellar journeys. In our own solar system, the Late Heavy Bombardment, a period of intense asteroid impacts on the Moon and Earth about 4 billion years ago, is thought to have been caused by the migration of the giant planets. Could a similar event in another star system have launched 3 Atlas into the cosmos? Its trajectory, which brought it into the solar system at an angle of 30 degrees relative to the ecliptic plane, suggests a chaotic ejection rather than a gentle nudge, hinting at a violent past in its original system. Its speed, over 30 kilometers per second relative to the Sun, made it one of the fastest moving objects ever. Observed, further supporting the idea of a forceful ejection, the comet's structural integrity suggests a minimal level of consolidation, perhaps analogous to what produced Kuiper belt objects in our own system. Its nucleus, estimated to be about 1 kilometer in diameter, appears to be surprisingly robust, despite its long and tumultuous journey. This resilience hints at a formation process involving slow, gentle accretion over millions of years. Similar to how Kuiper belt objects like Arakoth were assembled. Yet, unlike Arakoth, 3 Atlas bears the scars of its interstellar voyage. Micrometeoroid impacts, radiation damage, and the slow erosion of cosmic dust have left their mark on its surface. Its rotation period, approximately 12 hours, suggests it has remained relatively unperturbed by major collisions, preserving much of its original structure, the slight wobble in its rotation known as precession indicates subtle gravitational interactions with other bodies during its interstellar journey, hinting at encounters with unseen companions. Its exact origin remains anonymous, one of countless planetary systems orbiting stars scattered through the galaxy. The Milky Way alone contains an estimated 100 billion stars, each potentially hosting its own family of planets and small bodies. Among these countless worlds, 3 Atlas's home remains unknown. Its trajectory, carefully traced by astronomers, offers no clear clue to its point of origin. It did not come from the direction of any nearby star, nor does its velocity match the motion of the stars in our galactic neighborhood. Instead, it seems to have wandered the galaxy for so long that its path has been randomized, erasing any memory of its starting point. Models suggest it may have traveled for as long as 500 million years. Crossing countless light years and passing through regions of star formation and stellar death, each leaving faint traces in its chemical makeup. Its path may have taken it through the Milky Way's spiral arms where massive stars explode as supernovae, enriching the interstellar medium with heavy elements that were later incorporated into 3 Atlas's icy structure. Known. 3 Atlas formed in a cold outer region of a planetary system with giant planets. Its composition and structure provide compelling evidence of its extrasolar origins, making it a unique messenger from the depths of the cosmos. Its orbit, unbound to our solar system, confirms it as the first observed interstellar comet, distinct from the asteroidal Oumuamua detected in 2017. Unknown. Which star did it come from? Despite extensive analysis, the identity of 3 Atlas's parent star remains a mystery, leaving astronomers to wonder about the countless other interstellar objects that may be silently crossing the void between the stars. Statistical models suggest that at any given time, there could be thousands of such objects passing through our solar system, most too small or distant to detect. Some may be as small as a few meters across, while others could rival the size of dwarf planets, all drifting through the cosmos like silent messengers from distant worlds. The origin mystery is just the beginning. It points to even more profound questions about the diversity of planetary systems and the small bodies they produce. If 3 Atlas is a representative sample, it suggests that icy, comet-like objects are common in the outer reaches of other star systems. These objects, forged in the frigid darkness beyond their parent stars, could number in the trillions across the galaxy. Each one is a potential time. Capsule, carrying the story of its birth and the conditions of its home system. As we unravel the secrets of 3 Atlas, we take the first steps toward understanding the vast and hidden population of interstellar travelers that drift through the cosmos. Its study has already inspired new missions, such as the proposed Comet interceptor, designed to rendezvous with interstellar objects as they pass through our solar system. Future telescopes, like the Vera C. Rubin Observatory, will scan the sky with unprecedented sensitivity, potentially detecting dozens of interstellar visitors per year, each offering a new glimpse into the cosmic neighborhood beyond our solar system. Part 9. The Interstellar Connection. What if the most extraordinary objects in the universe are the ones that connect us to the cosmos beyond our sun? The vast, unexplored territories between the stars have long been a source of fascination, but only recently have we begun to glimpse the visitors that traverse these abyssal distances. These interstellar travelers, fragments of distant worlds, offer us a direct line of inquiry into the processes that shape exoplanetary systems, light years away from our own. 3 Atlas is not the first interstellar visitor. In 2017, Oumuamua defied expectations with its elongated shape and lack of detectable cometary activity. This cigar-shaped object, measuring approximately 800 meters in length, was unlike anything astronomers had ever observed. Its tumbling motion and mysterious acceleration, which could not be explained by gravitational forces alone, sparked intense debate. Some theories proposed it was a hydrogen iceberg, while others speculated it could be an artificial object, a remnant of an advanced civilization. Its journey through our solar system lasted mere weeks, but its impact on our understanding of interstellar objects will endure for generations. In 2019, Borisov looked and acted like a typical comet, displaying activity and composition similar to solar system comets. With its familiar coma and tail, Borisov seemed almost ordinary compared to Oumuamua, yet its origins were anything but ordinary. Travelling at a blistering 33 kilometers per second, Borisov was clearly an interloper, its trajectory unbound by the gravitational influence of our sun. Its composition, rich in carbon monoxide and water ice, mirrored that of comets born in the outer reaches of our own solar system, suggesting that the processes that form comets may be universal across star systems. Now, 3 Atlas pushes the boundaries of cometary behavior with its intense activity and potential for extreme mass loss. First detected in 2023, this object has captivated astronomers with its prolific outgassing, releasing vast clouds of material as it approaches the Sun. Its nucleus, estimated to be no larger than 1 kilometer in diameter, seems to be disintegrating at an alarming rate. Some models predict it could lose up to 50% of its mass during its closest approach to the Sun, a spectacle that promises to redefine our understanding of cometary volatility. Observation: each interstellar visitor has been unique, displaying a diversity of characteristics that defy simple categorization. Oumuamua's elongated shape and mysterious acceleration, Borisov's familiar cometary behavior, and 3 Atlas's explosive activity paint a picture of interstellar objects as varied as the stars they come from. This diversity challenges our preconceived notions of what an interstellar object should look like, forcing us to re-evaluate the models we use to understand these cosmic wanderers. Speculation: could this diversity hint at the wide range of formation environments and processes operating in other planetary systems? The conditions that gave rise to Oumuamua, Borisov, and 3 Atlas may be as varied as the objects themselves. Perhaps Oumuamua formed in a system where icy bodies are sculpted into elongated shapes by tidal forces, or where advanced technologies leave behind remnants that wander the galaxy. Borisov's familiar composition suggests it may have originated in a system not unlike our own, where comets form in the cold, distant reaches of a star's gravitational influence. 3 Atlas, with its explosive behavior, may hint at more chaotic formation processes, where cometary bodies are subjected to extreme thermal or gravitational stresses. The interstellar connection is just the beginning. It points to even more profound questions about the nature of planetary systems and the small bodies they produce. Are the processes that shape our solar system unique, or are they echoed in the countless star systems that dot the Milky Way? Do all planetary systems produce small bodies like comets and asteroids? And if so, how do their properties vary from one system to the next? The answers to these questions may lie hidden in the trajectories and compositions of future interstellar visitors, awaiting discovery by the next generation of telescopes and astronomers. As we continue to study these interstellar objects, we are not just learning about distant star systems. We are also gaining insight into our own origins. The small bodies that populate our solar system, from comets to asteroids, are thought to be remnants of the primordial disk of dust and gas that gave birth to our planets. By comparing these objects to their interstellar counterparts, we can piece together a more complete picture of how planetary systems form and evolve. This interstellar connection reminds us that we are part of a vast, interconnected cosmos, where the stories of distant stars intertwine with our own. Imagine the day when our telescopes detect not just fragments of distant worlds, but entire exoplanetary systems in the process of formation. We may witness the birth of comets and asteroids around other stars, observing the same processes that shaped our own solar system billions of years ago. Such discoveries would not only deepen our understanding of the universe, but also inspire a new generation of explorers, dreaming of the day when humanity might follow in the footsteps of these interstellar travelers, venturing beyond our solar system to explore the cosmos firsthand. Until then, we watch and wait, our eyes turned to the sky, as the universe continues to send its emissaries across the void. Each interstellar visitor is a messenger from the depths of space, carrying with it the stories of distant stars and the promise of discoveries yet to come. Part 10. The Cosmic Legacy. What if the most extraordinary objects in the universe are the ones that leave us with more questions than answers? The cosmos is vast and full of enigmas, but few have captivated astronomers quite like 3 Atlas. This interstellar traveler, a messenger from the depths of space, has left an indelible mark on our understanding of the universe. Its journey through our solar system was brief, spanning a mere few weeks, but its impact will resonate for generations. As it traversed our cosmic neighborhood, it offered scientists a fleeting yet unprecedented opportunity to study an object born beyond the reach of our sun. 3 Atlas is already receding, moving away from the Sun at a staggering speed of over 30 kilometers per second. As it fades from view, it carries with it the secrets of its origin and the story of its journey. But the questions it raised and the data it provided will keep. Researchers occupied for years, gradually revealing what this unexpected visitor taught us about the cosmos beyond our Sun. Its trajectory, hyperbolic and unbound by the Sun's gravity, is a stark reminder of the vastness of the universe and the endless possibilities it holds. The faint glow of its outgassing tail, visible only through the most powerful telescopes, serves as a final farewell, a cosmic wave goodbye before it disappears into the interstellar. Void. Observation. The next generation of survey telescopes, like the Vera Rubin Observatory, will likely discover interstellar objects routinely. With its 8.4-meter mirror and 3.2 gigapixel camera, the Rubin Observatory will scan the entire visible sky every few nights, cataloguing countless celestial objects. Among these, interstellar visitors like 3 Atlas will no longer be rare anomalies but regular occurrences, adding to our understanding of the diversity of small bodies in the galaxy. Each discovery will be a new piece of the cosmic puzzle, helping us map the unseen landscapes of the Milky Way. By some estimates, these advanced telescopes could identify up to 1 interstellar object per year, building a database of these enigmatic travelers and their properties. The Rubin Observatory, set to commence operations in 2024, will revolutionize our ability to detect and track interstellar objects. Its legacy survey of space and time, LSST, will capture over 800 panoramic images each night, creating a cinematic record of the dynamic universe. This unprecedented dataset will allow astronomers to trace the paths of objects like 3 Atlas with unprecedented precision, revealing subtle changes in their trajectories that could hint at gravitational interactions with unseen celestial bodies. Over its 10-year mission, the Rubin Observatory could catalogue hundreds of interstellar visitors, each one contributing to a richer understanding of the galaxy's composition and history. Speculation. Could 3 Atlas transition from being a unique curiosity to being one example in a growing catalogue of interstellar visitors? As our detection capabilities improve, it is estimated that we could identify dozens of such objects in the coming decades. Each one will bring new insights into the composition, dynamics, and origins of interstellar material. The possibility of studying these objects up close, perhaps even sending dedicated missions to intercept them, could revolutionize our understanding of the galaxy and our place within it. Imagine a future where spacecraft equipped with advanced spectrometers and sampling tools could rendezvous with an interstellar object, collecting data that would rewrite textbooks and inspire new theories about the cosmos. In the not-too-distant future, NASA or other space agencies might launch missions specifically designed to intercept interstellar objects. These spacecraft, equipped with state-of-the-art instrumentation, could analyze the composition of these visitors in situ, providing invaluable data about the building blocks of distant star systems. For instance, a spacecraft could use mass spectrometers to determine the isotopic ratios of elements in an interstellar object, revealing whether it formed in a system with a different chemical composition than our own. Such missions could also deploy landers or impactors to study the object's surface and subsurface, uncovering clues about its formation and evolution. The cosmic legacy of 3 Atlas is just the beginning. It points to even more profound questions about the nature of the universe and our place within it. Did 3 Atlas originate in a system vastly different from our own, perhaps around a red dwarf star or a massive blue giant? Did it form in the chaotic aftermath of a supernova explosion, or was it ejected from a planetary system during a catastrophic collision? The answers to these questions could redefine our understanding of planetary formation, stellar evolution, and the dynamics of the galaxy itself. Its composition, rich in elements like carbon and oxygen, suggests it may have formed in a system where organic chemistry is prevalent, hinting at the possibility of life-supporting conditions elsewhere in the galaxy. Some theoretical models suggest that 3 Atlas could have originated in a binary star system, where gravitational interactions between 2 stars frequently eject small bodies into interstellar space. Alternatively, it might have formed in a protoplanetary disk around a young star, where collisions between planetesimals could have launched it on its interstellar journey. By studying objects like 3 Atlas, astronomers can test these hypotheses and refine their models of planetary system formation, shedding light on the processes that shaped our own solar system. 3 Atlas is not the first interstellar visitor to grace our solar system. In 2017, astronomers detected Oumuamua, a cigar-shaped object that puzzled scientists with its unusual shape and tumbling motion. Unlike 3 Atlas, Oumuamua showed no signs of outgassing or comet-like activity, deepening the mystery of its origins. 2 years later, in 2019, the comet Borisov was spotted, marking the second interstellar object ever observed. Borisov, with its distinct coma and tail, resembled a typical solar system comet, yet its trajectory confirmed it was an interloper from another star. Together, these 3 objects, Oumuamua, Borisov, and now 3 Atlas, form the foundation of a new field of study, interstellar object research. As our detection methods improve, scientists anticipate discovering even more interstellar objects in the coming years. Each new visitor will bring fresh insights into the diversity of celestial bodies in the galaxy. Some may be rocky and asteroid-like, while others could be icy comets rich in water and organics. A few might even defy classification. Challenging our understanding of what interstellar objects can be, the European Space Agency's upcoming Comet Interceptor mission, designed to study pristine comets or interstellar objects, could revolutionize our knowledge of these enigmatic travelers. With its 3 spacecraft, a main probe and 2 smaller secondary probes, the mission aims to provide a comprehensive view of these objects, from their composition to their internal structure. The Comet Interceptor mission, scheduled for launch in 2029, will be strategically positioned at the Sun-Earth Lagrange point L2, allowing it to quickly respond to the detection of new interstellar objects. Once a suitable target is identified, the spacecraft will embark on a trajectory to intercept the object, conducting a flyby at close range to gather detailed measurements. The mission's instruments, including cameras, spectrometers, and dust analyzers, will provide an unprecedented view of the object's surface features, composition, and activity. By studying multiple interstellar objects, the Comet Interceptor could reveal whether these visitors share common characteristics or represent a diverse population of celestial bodies. Finale. Final countdown. As 3 Atlas fades into the darkness, it leaves behind a trail of unanswered questions. Did it lose 10% of its mass during its closest approach to the Sun, or is that estimate too high? What is its rotation state, and does it explain the observed activity patterns such as the periodic outbursts of gas and dust? Does the complex ion tail structure vary with time, reflecting changes in solar wind conditions or intrinsic changes in outgassing? And, most tantalizingly, did any spacecraft fly through the tail and collect direct composition data, revealing the chemical fingerprints of another star system. These questions will keep researchers occupied for years, gradually revealing what this interstellar visitor taught us about the cosmos beyond our sun. But one thing is certain. 3 Atlas came from another star system, spent a few brief weeks in ours, and is now leaving, never to return. Its trajectory will carry it into the interstellar void, where it will drift for millions of years before perhaps encountering another star. System. Yet the questions it raised and the data it provided will keep researchers occupied for years, gradually revealing what this unexpected visitor taught us about the universe we inhabit. And so we watch and wait, knowing that out there in the darkness between the stars, more visitors are travelling toward their own eventual encounters with our solar system. Each one will carry new questions and new answers about the cosmos beyond our sun. These future interstellar objects could be even more extraordinary than 3 Atlas, perhaps harbouring organic molecules, water ice, or even remnants of extraterrestrial life. The possibilities are as limitless as the universe itself. Some may originate from regions of the galaxy where stars are densely packed, increasing the likelihood of dynamic interactions and ejections. Others might come from the distant outskirts of the Milky Way, where star formation is slower and conditions are more serene. 3 Atlas came from the stars, and to the stars it returns. But its legacy will remain, a testament to the endless mysteries of the universe and humanity's unquenchable thirst to understand them. It is a reminder that we are not alone in the cosmos, not in the literal sense of extraterrestrial life, but in the profound sense that we are part of a vast interconnected web of stars, planets, and interstellar wanderers. As we continue to explore the universe, 3 Atlas will stand as a milestone, a moment when we glimpsed the infinite possibilities of the cosmos and dared to reach for the stars. In the decades to come, 3 Atlas will become a cornerstone of astronomical research, its name etched into the annals of scientific history. Future generations of scientists will study its data, refining their models of interstellar objects and the processes that shape them. Its journey through our solar system will be replayed in simulations, revealing new insights into its behavior and composition. And perhaps one day a spacecraft bearing the name Atlas will embark on its own interstellar voyage, inspired by the object that once passed through our cosmic neighborhood and left us dreaming of the stars. The Breakthrough Starshot initiative, announced in 2016, aims to send a fleet of tiny spacecraft to the Alpha Centauri's star system, our closest stellar neighbor. Though still in its early stages, this ambitious project represents humanity's first steps toward interstellar travel. If successful, the nanocrafts propelled by ground-based lasers could reach speeds of up to 20% the speed of light, allowing them to traverse the 4.37 light-years to Alpha Centauri in just over 20 years, while 3 Atlas will be long gone by then. The technology developed for Starshot could one day enable us to chase down other interstellar visitors, exploring them up close and unlocking their secrets. As we stand on the cusp of this new era of discovery, 3 Atlas serves as both a herald and a challenge. Its brief visit has opened our eyes to the wonders of the interstellar realm, reminding us that the universe is far stranger and more beautiful than we can imagine. But it also challenges us to push the boundaries of our knowledge, to innovate and explore, and to embrace the unknown with curiosity and courage. In this way, 3 Atlas is not just an object of study, but a symbol of our collective aspiration to understand the cosmos and our place within it. It is a beacon, guiding us toward a future where the stars are within our reach, and the mysteries of the universe are ours to unravel.